And our next speaker is Yishan Wu, who is with CISPA, a second-year PhD student.
Hello everyone, I'm Yishan Wu from CISPA, and today I'm going to present our paper, Link Stealing Attacks Against Inductive Graph Neural Networks. And this is a joint work from with researchers from CISPA, Hong Kong University of Science and Technology, University of Birmingham, University of Lausanne, and Duke University. And let's get started. And nowadays, machine learning models are playing crucial roles in our daily life. One of the key factors for them being so successful is the data. Only with a huge amount of data, it can power tons of real-world applications for us to use. And among of these data, there are a special type of the data that comes naturally in the format of graph. The graph data basically contains the nodes and edges that connect these nodes, and making it different from those data that is independent of each other, like the image data. And to take full advantage of this graph data, researchers create a special type of neural network called graph neural networks. The core idea of the graph neural network is to leverage the neighbor information observed among nodes to learn embeddings to perform the downstream task. Here in the paper, we talk about the node classification task. Here, the graph neural networks learn the node embeddings to predict the labels of the given nodes. And we can implement the graph neural networks in two ways, transductive and inductive. Let's first talk about the transductive settings. And in these settings, the entire graph include the node attributes and edges can be observed during the training by the transductive GNNs, and only the labels of the test nodes are unknown. And during the inference, user only needs to feed the identifiers of these unlabeled scene nodes into graph neural networks and obtain the prediction results. And these transductive GNNs cannot be generalized to any new nodes, new graphs. They can only predict the label of scene nodes during the training. However, in reality, there are many real-world applications where the graph is actually evolving. So here comes another setting called inductive settings. During the training, only the training graph can be observed by the inductive GNNs. And during the inference, the users need to construct their own subgraphs, either a zero hop, which has almost no neighbor information, or several hops that there can include some levels of neighbor informations. Here we only consider one or two hop, which is very common in evaluations, and to obtain the predictions of these unseen test nodes. And from the above, we can see that there are differences from these two settings. The transductive GNNs are actually memorize the training graph and generate fixed embeddings for each node in the graph. And compared to this one, the inductive settings learns to generalize these node embeddings functions, which can apply to other new nodes, new graphs. So in this way, we can see the inductive graph neural networks are actually more generalizable and flexible for these dynamic real-world applications, especially like the social networks and recommendation systems, which are adding or deleting nodes and edges from time to time. And due to the prevalence of graph structure data, there exists some previous work shows that the privacy issue of this data in graph neural networks. And there is one previous work shows that the transductive GNN actually leaks the graph information, making it vulnerable to the link stealing attacks. What the link stealing attack focuses is actually a research question. It's like given two nodes used to train these black box graph neural networks. can we predict whether these two nodes are linked or not? Why this attack considers a privacy issues? In one case, social relationships, which are normally encoded by edges in the graph, often represent privacy-sensitive information among these social network users. So it actually naturally makes us wondering, what about the inductive graph neural networks, as it actually has a wider application in the real world, and the privacy issue in these inductive GNNs is necessary to be explored. But what are the challenges for us to apply these link stealing attacks against inductive graph neural networks? Let's first see the transactive graph neural networks. It's like memorizing this training graph and generate a fixed embeddings for these scene nodes. But for the inductive graph neural networks, we are learning some generalizable embedding functions to generate embeddings based on the given subgraph, the one user needs to construct. So in inductive graph neural networks might not be that much vulnerable to these link stealing attacks because they are not learning some specific information of the training graph. And another challenge is that the adversary needs to construct their own subgraph as a query to the inductive GNNs. So which actually means that the adversary can only rely on some limited information, because the most important thing is here the neighbor information for the link they want to intend is always missing. So the subgraph information is always incomplete. And for the transactive GNNs, we notice that the adversary only queries with the identifiers and to get the fixed embeddings and learn during the training. So it means that they're actually using the full neighbor information to generate these node embeddings. While for the inductive GNNs, the adversary actually queries with their own constructed graph. It depends on how much knowledge they can have for the training graph and obtain the node embeddings based on these subgraphs. Now let's look at our threat models. The adversary can construct the graph, subgraph based on their own knowledge, either zero hop with no neighbor information at all, or 1 or 2 hop with limited neighbor informations. And having these subgraphs, the adversary can choose to have or not having these 3 types of features, no features and posterior features from the inductive GNNs, and some traditional graph feature like the common neighbors. And from these results, we can see that the proposed link stealing attacks actually performs very good in all cases, like most of them are surpassing 80%, and especially for the cases where no neighbor information is provided, it can achieve a good result. And meanwhile, from the left to right, we can see here the adversary leverages more information to enable the link stealing attacks. And indeed, more information from left to right, it can achieve a better performance. And as the final conclusions, we propose in total 10 link stealing attacks against these inductive graph neural networks. And from the previous table results, we can see that there is no neighbor informations. Even if there is no graph neighbor informations, our attack still achieves a very good performance. And with more information, like combining the node features or traditional graph features to enable our link stealing attacks, it can indeed achieve a better performance. And finally in our paper, there are also some other experiments shows that the higher robustness of our attacks and better performance than some traditional link prediction methods, and showing that these inductive graph neural networks actually indeed leak privacy informations. And if you do want to know more detailed evaluation results, please check out our papers. And that's it for the presentation. I'm happy to take your question.
Yes, if there are questions in the audience. And I can start with one for you. So for some of the data sets you considered, could you just talk through maybe what an attack would look like if it was being implemented, like how the queries are being made, and maybe like who's holding the model in those cases? I was interested in like the PubMed data set, for instance. Like, could you speak a little more about how, like, give an example maybe of what would be learned in that case and who would be holding onto the model that the adversary is querying?
The adversary will first like train a shadow model, which like mimics the behavior of the target model, and then they should have first the two nodes with the node attributes, and like as a basic informations. And if they do not have any graph information, like what I said here, zero hop, they need to like build a self-loop edges. So these two nodes can be considered as a subgraph to fit into the graph neural networks and obtain the posteriors. It's like the prediction results from the graph neural networks. And with this information, just the posteriors, we can infer whether these two edges are linked or not. And for the PubMed cases, here we can see the A0 is actually the results for the zero hop, like no graph information, and it achieves a pretty good, I would say.
Okay, great, thanks. And I'm wondering, did you consider defenses in this work? So you showed
Yeah,
a lot.
sure.
Oh, yeah.
Yes, we do have two defenses, like some state-of-the-art defenses for these graph neural networks, like differential privacy, and we found that if we only have a like tiny, if we want to achieve a good defense performance, we need to have a very high privacy budget. So it considered not in practice, it cannot work in practice.
Okay.
Yes.
Any other questions in the audience?
Thank you for the presentation. I'm Son from Arizona State University, and I want to ask you to elaborate further on what kind of information does the attacker have? Does he have the information about the training graph, or he just have the graph node that he wants to query?
It just has a graph nodes. And if we can, you can see here, we actually consider three more scenarios. First, you need to have the node attributes. That's like must-have information. And then you can, based on your own knowledge, to build the subgraphs. If no subgraph information, then zero hop. If you have some limited information like one hop, you can add it on your own, build your own subgraphs, and fit to the graph neural networks. It's like basically, it depends on how much you have. You can add it all on your subgraphs and do the query.
So the node in the subgraph doesn't need to be coming from the training data.
If you want to infer if there is a edge in the training graph, the first thing is you need to know the training nodes. Then you can consider if they have the connection edges.
Thank you.
Yeah.
And any other questions for Ishin? Okay. Thank you very much, Ishin.